Okay, so we have another interesting topic today, angular momentum. So in linear terms, again, rotation just puts an R, it puts a position vector with everything, right? Absolutely everything. Torque has a position vector with force, right? So force with a position vector gets you torque, right? Omega, that angular speed, is really just, omega times your position vector times your radius gets you your velocity, your linear term, right? And same thing for your acceleration, right? Your acceleration, so V is omega times R. Acceleration tangential, right? The acceleration you experience out here, if it's going faster and faster and faster and faster around on the outside, that's going to be equal to your alpha times your R, and that's basically how fast you're going around if you're speeding up this way, right? So your alpha is your angular acceleration, right? Angular acceleration times R gets you your tangential. And our torque, we found out that was a cross product. That was an interesting one. It was your position vector across your force, okay? And now we're going to do another one, which is linear momentum. It's going to be our position vector cross our momentum. So that's where we're going to start here. Okay. So if you remember, linear momentum, how much momentum this marker would have if I threw it, right, would be, it's a vector, right, because it has a direction with that velocity. It can be going this way or it can be going that way. It could be positive, it could be negative. It was the mass of the marker times the velocity, and the velocity is the thing that gave us the direction. So that was our linear momentum. Well, now our angular momentum, again, has no m in it for momentum at all, okay, because why? So L is now our angular momentum, okay? Angular momentum, see if I can fit that in there, is L. There we go, slightly better arrow, okay. So L, and L, again, we're going to do, just like I showed you with torque, right? We're going to put a position vector on it and cross product with momentum, okay? So we're just taking the linear version and crossing it with R. That's pretty much it. That's what you do for most of this stuff, okay? So the weird thing is, if you remember momentum was conserved in any kind of a collision unless we take and put impulse into it, unless we push it from the outside, right? Momentum was always conserved. If I throw this thing, it's going to continue on with the same velocity forever, right? If it has another object in the same system, those two markers come and hit each other, same mass on either side, they come and collide and they hit, they're just going to stop and fall down because they'll have no velocity left, because plus velocity and minus velocity will cancel out to be zero velocity. Angular momentum must also be conserved then, right? If momentum was conserved, angular momentum should be conserved too. All we're doing is just adding a position vector, correct? Well, that's a weird question. It is conserved, but only in very certain situations. Okay, so let's take a weird example here. I'm going to throw an object into the air like so. Okay, give it a parabolic trajectory here. Look at that, even caught it. Okay, so if it goes across like so, I got person A standing here. Person A, hello. And here's person B. Hello. I got hair. Okay, it's really late at night, guys. Just don't judge me too much. All right, person B. They're both going to look at this object as it's being thrown. It's being thrown from here to there. Okay, so here is our marker. Okay, and it's going this direction. Later on, okay, so this is time is equal to, let's say 1. Here is time 0, right? 0 seconds, 1 second. And over here at time, I don't know, let's say 3 seconds, right? Whatever. Our marker is all the way at the other end, flying towards this person. Okay? And it's right at the end of its path. All right? So, let's do linear momentum here, R cross P, okay? And let's break this down even more, okay? So momentum, we can break that down, okay? L is going to be the same as our position vector, why I put equals in twice, I don't know. Okay, our position vector times our mass times velocity, right? That's momentum. So we can get L is equal to m times r cross v. Okay, and so let's look at what happens here. If we go from here, mass doesn't change the whole way. Well and good, okay? The velocity, it might change, but let's just assume for now, okay? Just for now, here and here, sorry, at 0 and at the end, it's got the same velocity, okay? Plus and minus, it'll have a different direction, okay? But in the x direction, it's always gonna have the same velocity going this way, okay? So if we're only looking at, let's say, the x component of it, velocity sub x, it'll actually have the same velocity the whole way. The y may change, but the x will not. So if we look at the x component of this thing here at 0, okay, that position vector from this person to there, their r is equal to 0, right? So no matter what you do, now you've got 0 in there, 0, 0, 0 for x, y, and z, okay? You're going to have 0 for your angular momentum. But let's take a look at it from point of view of person B. Their position vector to here is going to be a real value. It's going to be an actual number, right? Maybe 10 meters, who knows, okay? But that number is actually going to be a real number up here. So you're not going to have a 0, you're going to have some kind of a value for it. And that's really strange. So if you're looking at an object from the outside, something that is being thrown, its angular momentum is not at all conserved. Not even remotely. But what if, and vice versa also, right? If we look at the marker over here, this is 0 distance away from this person, so he's going to have 0 angular momentum there. And it will have had a value here without having anything interrupted or interact with it, really, right? So momentum in here, angular momentum here is not conserved. It's weird, okay? But if we look at a different case, what if we set ourselves in a special place? Okay, we're going to set ourselves at the center of things, right? We're going to be egocentric. If you are the sun, right, and here's the earth out here, or if you're, center of the wheel and everything's spinning around you, right? Whatever you want to look at it, okay? You're going to have a velocity like this. And that velocity, you're going to have L is equal to R, your position vector, which will be here. Okay, there's your R, cross your momentum, mass times velocity, right? So mass is not going to change the whole way. So really we have to look at the V here. The V is up, okay, and our R is over. So great, we got an actual angular momentum, right? But if I look at it here, okay, if I look at it sometime later on, I've got an R that's actually the same value, okay? And I've got a V, except for this value is now up instead of over, right? And I have a V that is now pointing in this direction. So guess what? It ends up being the same number. If you're at the center of things, if you're at the center of rotation, your angular momentum is absolutely conserved, but only if you're at the center of rotation. So, for this, if you're sitting at the center of this wheel, and the wheel is turning around you, angular momentum is conserved. If, on the other hand, you're on the edge of the wheel, and the wheel starts to turn, angular momentum for you is not conserved. Because you are constantly changing your point of view. From here to the other edge of the disc, it's going to be changing, right? If you're sitting on the edge of the disc, right, better yet, you start taking and moving the disc like this. If you're where my hand is, then great, your angular momentum is conserved. You're at the center point, you're at the center of rotation. But if you're here at the center of the wheel, right, and I start doing this, your angular momentum is not the same because your position vector to any point on the wheel is changing as you go, relative to some other rotational point. So, that is interesting, okay? But most of the questions we're going to come across, we're going to be at the center of things, okay? So as long as you're at that center point, angular momentum is conserved. All right? So if you're a planet, and this is interesting, okay? So planets are strange beasts because those things, they actually change. They change their velocity because a lot of planets actually don't have circular orbits. The farther you go out, the more elliptical they tend to become, right? So over here, their velocity is smaller, but their radius is much larger. Over here, where they're really close by, or sometimes, a lot of times they have like a close, they have apogee and perigee, right? Para meaning close by. So if you're here, on the other side of this, you've got a really small r. So what do you think has to be true of your velocity at this point? It's got to be a lot larger. But when you multiply those two as a cross product, right? R times mv, right? You will actually get the same value. So your angular velocity will still be conserved even if you got some crazy electrical path. As long as you're at the center of rotation, you're good to go. All right, but just like we did with torque, okay, so there's kind of the main concepts, but just like we did with torque, let's not leave this here. Okay, a more useful version of this most of the time for us is going to be this. Instead of looking at the actual cross product of the thing, right, R cross P, what we're going to want to do most of the time is actually find the magnitude of this thing. All right, I put two absolute values on the outside because you have to account for both direction as well as, you know, two vectors basically. Okay. So when we try to find the magnitude of this, it's going to be like what we got for torque, R times momentum times sine theta. Okay. So if you have some kind of a motion like this, right, your velocity like so, right, mass doesn't have a direction. Velocity like so, R like so, you can figure out the magnitude of your angular momentum by doing R times the momentum, or times m times v, times sine theta. A lot of times, most of the time, that angle there is going to be 90 degrees. Is it possible that that angle could be different? Yeah, I mean, it's possible that you could have something kind of flying off at some kind of a weird angle, and you'd have an R like that at some moment in time, and your angle would actually be different than 90 degrees. That's entirely possible, just like it is with torque, okay? But most of the time, you're going to have a wheel or something that's in an orbit, so your velocity is going to be perpendicular to or at 90 degrees to your R, okay? And so you're going to end up with this formula for your angular momentum. And I'll show you a demonstration video with angular momentum that I think you're going to like. It's pretty cool. It shows you how things are conserved. Pretty neat, actually. I'll give you a little hint right now. Ice skaters, okay? Figure skaters.